Welcome everyone to 11.4, the comparison tests. So there's two comparison tests, the direct comparison test and the limit comparison test. The direct comparison test will be very similar to what we had for integrals, right? We talked about when do improper integrals converge or diverge. It'll be something very similar for this, for series. And then we have the limit comparison test, which is more difficult to prove, but it's a stronger theorem, at least in my opinion. So, and then finally, of course, we will apply the comparison test once we understand the statements of these things to a variety of series problems. So let's get to it with what is the direct comparison test. So let's suppose I have these two series, a sub n and b sub n, and the claim is that if the series with the b sub n terms is convergent, and a sub n is less than or equal to b sub n for all n, and remember these are positive terms here that we're dealing with, that's the only condition really, then the series with the a sub n terms is also convergent. Now, if the series with the b sub n terms is divergent and a sub n is greater than or equal to b sub n for all n, then the series with the a sub n terms is also divergent. So this is saying if the big one converges, then the small one converges. And if the small one diverges, then the big one diverges. Now with the limit comparison test, again, we need positive terms, but now we're going to be dealing with a limit here. So this is looking at the limit of the ratio of a sub n divided by b sub n as n goes to infinity. And if this is equal to some c, where c is a finite number that's greater than 0, then either both series converge or both series diverge. Their fates are tied together. All right, so let's try to apply both the direct comparison test and the limit comparison test to this problem here. All right, so for the direct comparison test, let's stare at our series a little bit closer. I really would like that -1 not to be there. So that's to say I'd like to compare this thing to 4 over 3 times n. The reason why I would like to compare it to this is because I know that this actually diverges. This is 4/3 times 1 over n, and by the p-series test, I know that this thing diverges. Okay, so if I want to apply the direct comparison test, and my conclusion is something's divergent, well then I'm in this second case here, right? And the second case says that you need to go out and find a smaller thing that's divergent, and then the bigger thing diverges. Okay. So I'm hoping 4 divided by 3n is smaller. And if I can, and I know that diverges, so hopefully that will show that my series diverges. Okay, so note, really quick, that 3n minus 1 is less than 3n. That makes sense, right? It's 1 less. So now if I do a little bit of cross division, essentially, it's cross multiplication in reverse, right? And 3n minus 1 and 3n are both positive numbers. So the inequality sign doesn't flip. And I get that 4 over 3n is less than 4 over 3n minus 1. Both of these are, of course, positive terms. So this one right here is indeed smaller, right? 4 over 3n is indeed smaller than 4 over 3n minus 1. So therefore, because the series 4 over 3n diverges. Why does it diverge? Well, it's because of the p-series test. So by the p-series test, so by the direct comparison test, the bigger series, which is 4 over 3n minus 1, must also diverge, right? We've shown that the smaller one diverges, and therefore the bigger one must diverge. All right, let's see how we would do this with the limit comparison test. So with the limit comparison test, the claim is we would use the same idea. So I'm going to let my an, so this is some different series here, my an be 4 over 3n. This is what I'm going to be comparing it to. Okay, 4 over 3n. Now my series is going to be the bn's, which is going to be 4 over 3n minus 1. And so I'm going to look at the limit, right? The limit as n goes to infinity of my an's divided by my bn's. There's my an's divided by my bn's. Oops, I forgot to write the limit as n goes to infinity. So there we go, the limit as n goes to infinity. Okay, so now we have a little bit of cancellation here, right? The 4's cancel, and instead of dividing by, let's see, 1 over 3 n minus 1. Let's go ahead and multiply by the reciprocal. So that's going to be the limit as n goes to infinity of 3n minus 1 divided by 3n. Okay, so how do I evaluate this limit? Well, I could just go ahead and distribute this divisibility by 3n. So if I went ahead and I distributed this, well, I'd have the limit as n goes to infinity of, well, 3n divided by 3n is 1, then minus 1 over 3n. So then as n gets very, very large, this just heads towards 1. So since this approaches a number c that's greater than 0, and it's a finite real number, we know that they either both converge or they both diverge. So since this series diverges, again, by the p-series test, we know that our series, 4 over 3n minus 1, must also diverge by the limit comparison test. So this limit comparison test essentially says that both of these series are somehow at the same level in some aspect. So we can compare them, and because we know one of them diverges, they both must diverge. Okay, so like I mentioned before in the intro of the video, that I think that the limit comparison test is stronger than the direct comparison test in many regards. Now, there are some rare problems out there that you can apply only the direct comparison test to, and it's harder to apply the limit comparison test. But in general, the limit comparison test is king. And so let me show you why. So let's go ahead, and in this case, I'm going to try to apply the direct comparison test. And so we're going to start off with, well, n squared is this thing that I'd want to compare it to, like forgetting about the n and forgetting about the plus 1. Let me just compare it to n squared. So n squared is less than n squared plus n plus 1. So now if we do this cross division thing, we'd have 1 divided by n squared plus n plus 1 is less than 1 over n squared. Okay? And now we know that, well, the series of 1 over n squared converges. Why? Well, the p-series test. So therefore, the smaller one must also converge. Right? These are positive terms. So again, the series 1 over n squared converges because of the p-series test. This is p equals 2 in our case. So by the direct comparison test, we've shown that our series converges. So again, we're always stating which tests we're using here. This is how we're showing our work. Okay, now let's try this again with part B down here. This is very similar, but the claim is that the direct comparison test will not work. So if I went ahead and I started to try to compare it to something, well, again, the natural thing to compare it to is n squared. Right? So forget about the negative n, forget about the 1. And in our case, though, n squared minus n minus 1 is less than n squared. So now when I do our cross division thing, I get 1 over n squared is less than 1 over n squared minus n minus 1. But unfortunately, this is now smaller, right? 1 over n squared converges, but it's smaller. And a smaller thing converging doesn't tell us that the bigger thing converges, right? It might be too big, it might diverge. So really we would need some function over here to converge to prove that this thing actually converges. It does converge, by the way. It's just we don't have a good comparison, a good direct comparison. So this one does not work. However, thinking about the limit comparison test with the same idea, right? We want to compare it to 1 over n squared. That does work. So let me show you. So the limit comparison test, I'm going to use my ANs. The thing that I compare it to is 1 over n squared. And my BN is, well, my series, 1 over n squared minus n minus 1. And now let's go ahead and look at the limit as n goes to infinity of AN divided by BN. Well, again, instead of dividing by this fraction, let's go ahead and multiply by the reciprocal. So I get n squared minus n minus 1 all over n squared. And now we can distribute this n squared. So I get 1 minus 1 over n minus 1 over n squared. And as n gets very large, this goes to, well, 1 minus 0 is 1. So again, this is a positive c value. So we've tied their fates together, right? So since the series 1 over n squared converges, again, by the p-series test, p is equal to 2 in this case, we know that our series converges. So our series is again 1 over n squared minus n minus 1 by the limit comparison test. So although we could not apply the direct comparison test with 1 over n squared, we can apply the limit comparison test. And in fact, if I was to take this, essentially just copy and paste here, back up for A, you can see that you could also apply the limit comparison test here. All I'd have to do is change these minuses to a plus. Minus to a plus, minus to a plus, minus to a plus, and then you get 1 plus 0 is 1. And there we go. So in fact, the limit comparison test seems to be stronger. All right, and I think that's probably a good place for us to take a break and stretch our legs here. My favorite thing about the comparison test, right, is that you don't have a lot of hypotheses, right? We don't need a continuous function. We don't need a decreasing. All we need is just positive terms. If you have that, you can apply the comparison test. All right, I'll see you next time.